Hello, science lovers. How are you guys doing today? Hope you guys are well. I'm just hanging out here. I have Booleanators producing, so yay! So I don't have to fret and worry about having nothing working. As I'm doing it, what happened last Saturday. Was it last Saturday or the Saturday before? We were talking about stuff, and my monitor was just like, yeah, OBS isn't going to pick it up today. So that's fun. So hopefully, I think you guys can hear me. All right, I hope you guys can hear me. So I've checked, and it seems like we're streaming on all the platforms, which is really, really awesome. So today we're going to talk about nuclear energy. So let's go ahead and get the slides up so we can kind of knock that out. Because this is one of the things that that's been in the news a lot, particularly with that HBO special, Chernobyl. So we're going to basically break down all of this. So the questions that we're going to be answering, here are the questions we're going to answer. We're going to essentially talk about, go to the next one. So as far as nuclear energy, what we're essentially going to talk about is what is it? How does it work? What are the issues associated with it, and what are the criticisms? So it's really important that as we're going through this, that we kind of discuss, because this is a bit of a hot topic. People get really, really scared when they watch shows like Chernobyl and they learn about, the 3 Mile, the 3 Mile incident. And we're going to talk about the 3 major incidents associated with nuclear energy. And we're going to talk about what exactly happens when they split this uranium atom. Hey, everyone. Hello, hello. And if you have questions, please feel free to ask, because that's what we're here for. So let's go to the breakdown. So for the breakdown, essentially, what we're talking about nuclear energy is the very first station opened in the 1950s. Now, it provides approximately 11% of the entire world's electricity, with a little over 450 different reactors available. It's the second largest source of low carbon power. There are over 50 countries that use approximately 225 research reactors, and it also uses uranium to make fuel. Good morning, guys. Hey, Geek Room. How you guys doing? Good morning. So let's see. Hey, Orla. So what we're going to do with this particular topic. Okay, so now let's dig in a bit deeper. Let's dive in a bit deeper about this. So when we're talking about all of it, all right, so when we're dealing with nuclear, for this talk, I honestly pulled so much information, and I got it from all kinds of different sources. Hey, guys. So the sources that I'm using are the worldnuclear.gov. I've pulled some stuff from Harvard, the New England Journal of Medicine, NIH, energy.gov, nuclear GE power. I also pulled some from EIA.gov, NEI.org. Medium has a great article about one particular prehistoric nuclear reactor. I'm going to talk about a prehistoric nuclear reactor. How cool is that? All right. So, and I have all of these websites listed at the end of this particular talk. You can also go on my website, scientistmel.com/resources, grab all these slides that I use, and kind of play around with them for yourself. Maybe give your own little nuclear talk with this information. All right, so what is nuclear energy? So essentially it's this. We split an atom of uranium into heat and steam. This then powers different turbines to generate electricity. Nuclear energy is considered one of the cleanest forms of energy sources available. Now let's talk about how a reactor works. So let me show you a bit of this. Before I do that, let me say hi to everyone. Hey, Doc Fearsome. Hello. I'm trying to catch up. If you guys have questions, please do hit me up. Hey, Nana. All right. Hi, Spooky. Okay, so let's talk about nuclear energy in our different. So we've got essentially a reactor core. So this is what we're working with. All right, so we have a reactor core, which is essentially a ceramic uranium oxide, and this is where the fission happens. So we've got fission going on here. And there are two different types of reactors. One is more common than the other. So the most common reactor is the pressurized water reactor. And then you have the boiling water reactor. Now, there's even been a prehistoric reactor. Is fusion considered nuclear energy? I don't think so. I haven't ever seen, and that's coming from Polgar 33. I haven't actually seen any information about fusion reactors. Perhaps, you know, I could do a whole show on fusion if you like. We can hop that in there. Hey guys, so pressurized water reactor, way more common than the boiling water reactor. And then you have prehistoric reactors. There was a prehistoric reactor that was found in Gabon, where there's a huge, or Gabon, I'm not certain how to pronounce that. So, you know, I say words wrong sometimes, so apologies for that. But Gabon, they found uranium deposits, and it was moderated, but essentially by percolating rainwater. All right, so the first thing we're going to talk about here is how fission occurs. What are we looking at? So let's go to this one. All right, yay. We doing good. All right, so for this particular image, I pulled this up off of the World Nuclear Gov site. So check or worldnuclear.org. Check that out. They've got really, really good, accessible, easy to read, broken down information to kind of help you with that. I'm glad you didn't miss it too, Nana. All right, so here we have two examples of fission of uranium, okay? So the isotope that they normally use is 235. Now, some of the 235 uranium in the reactor core is turned into plutonium, okay? And about half of this is fissioned similarly, providing approximately a third of that energy output that we see within a reactor. Now, the fission products in the ceramic fuel, you remember that says ceramic uranium, they undergo this type of radioactive decay. So they release a little bit more heat over time. Now, they are the main wastes from the process that we have. Now, this reactor core, it's not just hanging out, you know, it sits inside this steel pressure vessel. So the water around it remains liquid. So the operating temperature is over 320 degrees Celsius. So that's pretty freaking hot. Now, for steam, it's either formed above the reactor core, or it can be in separate pressure vessels. This steam then gets those turbines to run, and that produces electricity. So if you can kind of think of like the steam engines of the past, where they use steam to get those wheels to move, or you can think of it as like with dams, like the Hoover Dam uses water to get turbines to move. This uses steam. So what's the best lure for fission? Knowledge. Just dabble a little knowledge out there, Doc Fearsome, and you're gonna get that best lure for the fission. So in this case, after the core, within the core that happens, the steam is then condensed, and you have water, and it's reused. Isn't that lovely? The byproducts of the whole energy is water. We will get into what nuclear waste is here in a bit and what the most common forms are. So let's take a look at what these particular reactors look like. How about that? All right, here we go. Isn't this awesome? Again, from the same website. I felt like these particular images were pretty easy going. So what we have here, we got control rods here in the center. We've got our pressurizer. So this is the most common form of reactor. So this is the pressurized water reactor in this particular picture. So do you think nuclear waste is environmentally friendly? Okay, so for this particular talk, talk or in what we're discussing with these topics, and that comes from Polar 33. There are 3 different types of waste, and I'm going to get into what the most common is and what the biggest issue is with each particular one. You have heavy, intermediate, and light. So heavy, intermediate, and light. So we'll get into those here in just a bit. All right, so this particular design of pressure reactor, this is the most common. So it has the water as the primary cooling in this heat transfer circuit. Now it generates steam in a secondary circuit. Now the boiling water reactor, that's not as popular as the pressurized one. It makes steam in the primary circuit, right? That's right above the core. So I mentioned it's either pressurized or it's just released right above the core. The one that's released right above the core, the boiling water one, is the least popular. The pressurized one is way more popular. So though it's still, that particular, even though the boiling water one is least popular, it still kind of, uses water as the coolant and moderator, but just the way that it's contained is where it's different. One is pressurized in the second circuit, and then you have one that happens right above the reactor. All right, and the picture here is the pressurized version. Now, in order to keep your reactor efficient, because you want it to constantly be efficient and consistently making the energy consistent, as far as getting those turbines going. In order to maintain that, about 1/3 or half of the used fuel is removed every year or 2 to be replaced with fresh fuel. I don't think people realize that and I'll get into how much uranium is actually used. It's a teeny tiny amount, and it can last for a very long time. Now, with this pressure vessel and any steam generators, they are housed in a massive containment structure. Concrete, okay? And it's reinforced. This concrete is about 1.2 meters thick. So if you're not so keen on the metric system, a meter is about the length of one of those yardsticks. You know what I mean? So it's about a little over 3 feet, right? So think, if you can't deal with metric, a little over 3 feet in thickness of concrete. This is to protect. This is essentially to protect any neighbors if there's a major problem inside the reactor, and it also protects the reactor from external issues. So a 3-foot wall of concrete is extremely important. Now, because some of the heat is generated from this radioactive decay, even after they shut down the reactor, cooling systems are still provided to help remove this heat and maintain operational heat output, so it's not overwhelming. Okay, so I mentioned that there is a prehistoric bed of nuclear energy. Let's see. Is a nuclear reactor the size of a suitcase possible? I suppose, but I wouldn't recommend that. And you would still have to consider the amount of water and steam that's being generated. And then you have, again, I mentioned the 3-foot wall that's needed to protect from any type of issues. So I would say that would not be the best thing for just people in general. But, I guess that's a good question, just in case, what if somebody were to steal something like that? What is my take on thorium lifter technology? I'm not certain. I would have to kind of dig into that a bit. Hold on. I'd have to research that topic a bit more in order to think about it and, to have a good response. Let me add that to my list of topics, and I'll do a show on it. I'll do an entire show on it. And, so that's a good idea. I'll add it to my list. Thank you for that, Beach 8. All right, let's dig in a bit deeper. Well, no, not that. Let's talk about the next thing, the prehistoric the prehistoric bed here that we found and we're there. So this is what it looks like. This is the prehistoric bed that was found in the 1970s. Now, the world's first nuclear reactor operated in this naturally, in this particular natural deposit of uranium, which is what was approximately 2 billion years ago. And it's now Gavin. You're welcome, Beach 8. All right. So it was discovered in 1972 by scientists from, and I'll probably say this wrong because I'm not French, Pirolate or Pirolate or Pirolais, Pirolais, maybe that, uranium enrichment plant, and this particular plant is in southeast France. Now, this deposit of uranium has ore bodies within the Earth's crust, and it's essentially moderated by this percolating rainwater. Now, this concentration of uranium-235, which is the isotope that we use in our nuclear reactors, is so high, or was so high at the time, that it triggered a self-sustaining nuclear reaction. And so you had all of this rainwater, that was coming down, and then this level of service repository that you see along the sides. There's your cooler, your little cooling stuff. And then you have, like in the purple there, you have the actual uranium. So it's pretty freaking cool that nature has its own nuclear reactor in prehistoric times. So let's dig in a bit deeper and talk about some facts involving nuclear energy. And so I'll go ahead and I'll take some questions too. All right. When we're talking about nuclear energy, let's get some facts here. Let me catch up on some of the chat first. All right. Thorium-fueled molten salt reactors look promising. There's some info about MSRs on World Nuclear.org if anyone is interested. Thank you. That is all. And I too endorse that particular website because it is. I've pulled a lot of information from there, and I found it quite accessible and very easy to read. So you can check that out. They originally considered nuclear cars and planes, but the shielding weight made it impractical. Yes. 3 feet of concrete cars is not like the best thing for, all of that. It would probably go pretty slowly, I imagine. All right. There's terrestrial analogs all over the earth, a lot in Australia. Thank you, Cersei. It's pretty interesting, all of that. So let's talk about some facts surrounding nuclear energy. A single uranium pellet contains the same amount of energy as 3 barrels of oil, or 17,000 cubic feet of natural gas. So if you're looking at like a standard house, let's say a standard house is 1,500 cubic feet. That's a single 1-story house. So even 1,700 cubic feet, we could go that. So you're talking about 10 of those? 10 houses? 10 houses, essentially. So a single uranium pellet contains the same amount of energy as natural gas for 10 houses. Well, if they were all filled with that particular gas. There is no combustion involved in nuclear energy, so there are no air pollutants. Go figure, Each pellet, each one of those pellets allows up to 5 years of energy. So one little pellet of uranium, ceramic uranium oxide, has up to 5 years of energy. So, that's pretty amazing. Uranium is also the most abundant metal in the world, so it's easily a good source for energy. It also provides around-the-clock energy for many months out at a time without interruption. So that's also a good benefit when it comes to nuclear energy. Oh no, wait until the ancient alien theorist hears about this info. I'm not saying it was aliens, it was aliens. Is that what he's saying? Oh goodness. All right, I'm checking out. Hey, Wayne from Canterbury, England. Yeah, that is a lot of natural gas. And that is a lot of farts, bull. You're right there, hey. Uranium fever. Okay. All right, so what I want to do is I want to show you guys a pie chart, essentially, of the different types of energy and how it's used. So let's just see the breakdown for this. All right. So about 33.3% of the world still uses coal. And we're looking at this if there was 25,082 terawatt hours, I believe. So uranium for thorium is even more plentiful. Yeah, I'm going to dig into that, Beach. I'm going to add that to my list of things, and we'll definitely talk about that. All right, so when we're dealing with that many terawatt hours, we've got 38.3% is coal, 23.1% is natural gas. So still over half of our energy still comes from combustibles. That's not good, and I'll explain a bit more why in a bit. We have about 16.6% is hydro, 10% is nuclear. Then we go down to solar, wind, geothermal, and tidal. We've got 3.7% is oil and 2.3% is other. So I'm not certain what the other is. I wasn't able to pull that information, but the source comes from the electricity information from 2018. All right, let me show you another graph here. All right, so all uses nuclear. Well, in 2017, and this again comes from the same database for the energy, I believe it was what was the name? I'm going to pull the name up again. All right, I got it. So the IEA, which is the electricity information. Now, this is data from 2017. So we have 13 countries in 2017. They produced at least 1/4 of their electricity from nuclear energy. France gets approximately 3/4 of its electricity from nuclear. Then you look at Hungary, Slovakia, and the Ukraine, more than half of their energy comes from nuclear energy. Now, then you consider Belgium, Sweden, Slovenia, Bulgaria, Switzerland, Finland, and the Czech Republic, about 1/3 or more. South Korea, again, a little less than 1/3. Comes of their energy comes from nuclear. And while in the USA, UK, Spain, Romania, Russia, 1/5 of electricity is from their nuclear energy. Now, Japan is used to relying on nuclear power for more than 1/4 of its electricity, and it's expected to return to somewhere near that level. Now, keep in mind the terawatt hours here, the USA still generates a lot of power, and that's largely due to population. So when you're looking at these numbers, consider the populations of each country. All right, so let's dive in a bit deeper and kind of break this down on what we're talking about for this information. All righty, and I'm gonna catch up on the chat. All right, so are you sure it's not the Strategic Homeland Intervention Enforcement and Logistics Division? SHIELD. Mr. P, I am not an agent of SHIELD, although I think, that might be fun. That might be a fun job. Maybe not. Maybe that wouldn't be a fun job. I would want to work in the lab. All right. Yeah. So that 3% is just some guy named Jim being force-fed beans for natural gas. Poor Jim. Oh, you guys like my mug? Shout out to Shannon Q. She bought one and she posted a picture. So thank you for that. Hydro is clean but disrupts wildlife, fish migration, ecosystems, etc. You're right, Nana. And in discussing hydropower, you have to also look at the Colorado River and the Hoover Dam. the water with the Grand Canyon, that sort of thing, where the way that the dam has been put into place. It's a necessity now, but it has actually affected a lot of the flora and fauna within the Grand Canyon. And it's been quite counterproductive to that particular environment. So I have solar on my home, saves me over $100 a month on electricity. I want solar on my house, Beach 8. I really, really do. I live in an area where the Tennessee Valley Authority is in charge of all of that. And I know out in other parts of the country where the TVA isn't present in lobbying, you can actually rent solar panel systems. Kind of like you would a satellite TV service. And they come in, they install it, and you pay just a little bit, but Tennessee doesn't allow that, or the Tennessee Valley Authority doesn't allow that. So any place that they have control, which is a large portion of the South, they don't allow that rent to own solar panels. And the cost of solar panels put on a house requires, for most people, to get out and additional loan on their own mortgage in order to cover that. So it's quite difficult. Hey, Peter. Hey, everybody. Yeah, you like my mug? You too can get a mug and be a cam girl for science on scientistmel.com/shop. I also have a bag. So because I wanted to check the quality and make certain it came out. So yeah, so check it out. You can have a bag and support your love of the girls in science communication. So there you go. So yeah, I wish I could do solar on my house. So, hey, so I'm catching up on the chat. Every house should have solar panels. That would be a big positive. It really would. So there you go. All right, so the need for nuclear energy is becoming increasingly clear as we continue to demolish our environment with fossil fuels. Climate change is a fact. We are seeing permafrost not expected to defrost for another few decades. It's actually defrosting, particularly in Alaska. This is a recent thing that's come out. They weren't expecting this permafrost to thaw for like another 10, 20 years, but it's happening now. We have a carbon problem. We have a lot of carbon dioxide in the atmosphere. We have technology to counter all of this, and we can do it by shifting to nuclear and other renewable resources like solar. That would be an excellent and not difficult thing to set up. With over 450 nuclear reactors worldwide with little incidents, why is it that people are afraid of nuclear energy? Well, recent TV shows, including Chernobyl on HBO, show the dangers of nuclear, but this is not new information. Literally, everything can kill you. It's the statistics that matter so you can assess the risk. So let's talk about nuclear waste, accidents, and what the cons are. So Homer Simpson cons. Let's have a look at that. So what are these cons? All right. So what we're going to look at here is this waste. So yes, there is waste associated with nuclear energy. So that's something that's not going to go away. And there's 3 different levels: high, intermediate, and low. The radiation accidents, that's a concern. Radiation can cause, if you're exposed to it, dosage matters. So that's what's important. I said literally anything can kill you. And it's a matter of dosage, how much exposed to the thing. That's why people can develop tolerances for certain types of poisons. You can even develop a tolerance to anti-venom if you're bitten enough. So it's a dosage that matters. So radiation accidents are a concern. You have safety concerns. Security. How secure is this uranium? Because it could be used for very not nice things. We know we can split the atom and destroy a city. We've done that, Hiroshima. Natural disasters are a concern. You have to consider earthquakes. You have to consider, tsunamis, typhoons. Is that going to have any kind of effect on your nuclear? And also, you need better audits on safety. All right, Cersei says all of those cons can apply to coal and natural gas, hydraulic fracturing. Absolutely right. And I'm going to talk a bit about that too. There's lots of death every year that's associated with pollutants in the air. We're killing more people burning coal than we ever have with nuclear, and I'll talk about those statistics. So let's go to the 3 different types of nuclear waste. All right, so these 3 different types. I pulled this off again, that wonderful, wonderful website, worldnuclear.org. And so there's 3 different types of nuclear waste. The most significant high-level waste from a nuclear reactor is the used nuclear fuel left over after it has spent about 3 years in the reactor generating heat for electricity. So remember, that one little pellet can go up to 5 years. So the waste issue hits around every 3 to 5 years about where you're going to, handle it. Yeah, or mining. You're right, Cersei. Mining can be an issue too. All right. So after 3 to 5 years, you kind of have to, you got to do something with the waste. Now, low-level waste is made up of lightly contaminated items like tools and work clothing from power plant operation. And this makes up the bulk of radioactive waste. So the low-level waste is about 90% of the waste that we see from nuclear reactors, and it only has about 1% of radioactive content. Now, people get scared and they're like, radioactive stuff, that's going to cause cancer. There's a hospital nearby that uses radioactive chemicals in order to have it's kind of like CAT scans. So they inject radioactive chemicals into a cancer patient. Those radioactive chemicals have an affinity for cancer, attaches to the cancer, and it lights up on the instrumentation. So they're able to see just how big or how little a tumor is. You can be exposed to varying low levels of radiation and be completely fine. Now, the majority of waste is this low-level waste, which is the 90%, which are tools, clothing. These people are exposed to it. You have your Geiger meters in there. It's extremely low risk, but people get scared. So let's just say that dosage matters. Now, items that require disposal are the intermediate level. That's usually filters, steel components that are inside the reactor, and some of those effluents from this reprocessing. Now, generating enough electricity for one person produces just 30 grams of used fuel each year. So it's not that much. Now, the high level waste, now that's the 95% radioactive content. Only 3% of the waste that we see from nuclear is the high level kind. Now, that's the super scary radioactive content. That's the stuff that can make you really, really, really sick. And that's the actual waste from the uranium. So the actual nuclear waste that we are worried about is only about 3% of all of the overall waste when you consider the clothing, the personal protective gear, the tools, the filters, the components within the reactor, and then the teeny tiny little bit. Yeah, PET scan, Beach 8. Yes, that's right. You're right. Thank you for that. The word was escaping me. The PET scan is the one. The positron, electro. Oh God, it was just there. It was right there, and then it went away. Right there in my head.
I think you're looking for tomography.
Yes, positron emission tomography. That's right, Booleanator. Thank you. Positron emission tomography. They use the radioactive chemicals that attach to tumor cells and tumor tissue to where it lights up upon scanning. Thank you. I actually did read up a lot on that at one point in time when I was looking at working in radioactive, the positron emission tomography. Yes, because those particular radioactive chemicals release the positrons, and that's what they look for. And it's all like, there you go. Yes. Yay. Awesome. All right. So when we're worried about waste, we're not really worried about waste. You know what I mean? It's a thing, but it's a small thing. All right. So let's look at the 3 major incidents regarding nuclear reactors. So there's 3 big ones. And these are the ones that we worry about. We're like, oh my God, nuclear reactors. Okay, so bear this in mind. there are 50-year history of civil nuclear power generation. All right. Nana says, Mel, in theory, couldn't we dig deep enough in the Earth's crust where the temperature is high enough to boil water, basically that thermal energy anywhere in the planet? Possibly. I mean, you consider, the core of the Earth is hot. You could probably dig far enough, to where you could just have thermal. That's possible. Doc says, stupid question. No, we don't. If you're being silly, then we say silly questions, but we don't say stupid questions here. Melting metal doesn't destroy the radiation. If so, why? Melting, well, you got to keep in mind, that's just a physical change. You're not, and you can, with heat in some cases, rearrange the structure. I mean, essentially, that's what we do with metal. We try to melt it down. We add alloys to it. That's how we're able to form it into different things. You can rearrange some structure, some crystal structures, and rearrange the way that the atoms interact with each other within metal. But that doesn't necessarily get rid of the fact that you have an isotope for a particular metal like uranium, where it's emitting radiation. So we can get it to really freaking super hot, like well over 320 degrees Celsius, which is usually what the working nuclear reactor is. So you're able to break those uranium things down at that heat. So you are breaking it down, but the nuclear waste after that, that small amount is still radioactive because it still undergoes radioactive decay. All right. So let's talk. Good question, though. So I hope, and if I say something, I misstep sometimes. So let me know if you're like, wait, Mel, did you mean this? And I'm like, oh yeah, you're right. I have no problem owning my mistakes. So if I misstep and say something strange, let me know. Yeah, it doesn't change the atomic structure. You're right, Beach 8. All right. So the 3 significant accidents, the 3 Mile Island, that was about 1979. We had Chernobyl, which is about 1986. And then we also had Fukushima in Japan in 2011. So 3 major accidents that cause lots and lots of problems within the 50-year history. So let's talk about the 3 Mile Island. So that what we're dealing with that is in 1979, the reactor was severely damaged, but the radiation was contained and there were no adverse health or environmental consequences. So nobody died. The environment didn't get messed up. Nothing particularly awful happened in 1979 with the 3 Mile Island. So they learned from that. They got better, and we went without major horrible incident until Chernobyl in the Ukraine in 1986. Now, the destruction, what happened here was the destruction of the reactor was by a steam explosion. It killed 2 people initially, plus a further 28 from radiation poisoning that occurred within a 3 months' time. It did have significant health and environmental consequences. So the one in 1986 was pretty freaking awful. That wasn't so great. All right. And then more recently, about 8 years ago, Fukushima in Japan. There were 3 old reactors there. There was together with a 4th. They were written off after the effects of loss of cooling due to a huge tsunami that were inadequately contained. So natural disasters are an issue with some of these. There were no deaths or serious injuries due to the reactivity, though 19,000 people were killed by the tsunami. Nobody was killed there or had any serious injury from Fukushima. Nobody was killed or the environment, nothing happened with 3 Mile Island. The only massive one that was truly a problem was Chernobyl, and that was due to not having adequate safety measures in place to protect the surrounding villages. So let's dig into this and talk more about accidents. And I'm going to catch up on the chat. Let's see. I would love to take a tour of the safe parts of Chernobyl. Yeah, Geek Room. That would be kind of cool. You know, it's funny. The people for HBO have asked others to stop taking very awkward selfies and comical pictures at the Chernobyl site because they feel it's kind of disrespectful. Kind of agree with that. You know, that's like going to the Titanic exhibit and saying, "Hey, look, you know, here's some dead people clothes." You know, trying to make light of a horrible situation. So yeah, you got to kind of you know, be careful with that. So yes, so let's talk about this. All right, so it's important to note, and Cersei mentioned this earlier, that accidents occur in every single energy industry. Okay, you can have coal mine explosions, petrol tankers that catch fire. You can have people die from natural gas in their own home, carbon monoxide. You have oil spills and leaks that destroy the environment. There is a risk with everything. Every single industry has some sort of risk, at least the main ones that we're seeing. Minimizing the risk is key and central when it comes to nuclear energy. Safety issues involve ample security to ensure that the uranium is secured. Safety audits can help with identifying weak reactor issues as well as proper use of equipment. Natural disasters can be an issue. So placement of reactors in regard to earthquake faults, water sources, you know, oceans like typhoons and tsunamis, as well as areas that are subjected to other potential mitigating natural occurrences that could cause damage to a reactor as well. So it's important to take all of these into consideration when dealing with that. Radiation risks, radiation sickness, and long-term effects regarding cancer are determined on dosage amount of radiation. So the amount of radiation you're exposed to is going to determine whether or not you have long-term cancer concerns or any type of radiation sickness. And there are medications that they have to kind of help with that. Waste storage and minimizing accidents are central to ensuring reduction in health risks. And the safety measures that I've discussed will help reduce these risks of accidents. So let me check out the chat here. So, all right. They sell tours of Geek Room at Chernobyl. I agree, Mel. Yay, Doc. A new business venture for Elon, radioactive waste disposal, very possibly, and that's something that they're regularly researching. Hence, 225 research reactors. There are 225 of the approximately 450 reactors are research nuclear reactors, just as that being one of the main reasons. Accident in Seattle exposed 50 people recently. No excuses. All right, so give me that information, Richard, and I'll check it out. With reactors, oceans tend to be a good source of the water needed for turbines and cooling. That's also a fair point. You got one there, Berillion. Too bad Nevada backed off the deal to bury the nuclear waste deep in the free mountains there. I thought that was a great idea. Oh, that might have been. All right, so I have a graphic for you to check out when we're talking about combustion. So let's go to that picture. So when we're talking about combustion of hydrocarbons, what does that mean? Some of you guys would be like, I hear all of this, but I don't know what that means. So when we're talking about burning anything, whether it's methane or it's coal, you know, you use the carbon in your grill, hopefully, because I'm a charcoal person. I don't do gas grills. Nah. I do charcoal grills. So I'm contributing to global warming with my charcoal grill. Really, it's not that much. But if we use it in mass amounts to provide energy, this is how it breaks down on the chemistry. Let's look at natural gas, methane. You take methane, CH4, that's a carbon, 4 hydrogens. You add some oxygen, a bit of a spark to start the reaction, you end up with carbon dioxide, water, and energy. Every single combustion of any hydrocarbon, whether it's oil, coal, Methane, the result is always the same: carbon dioxide, water, and energy, usually in the form of heat. That's how that works. So, nuclear fission of uranium. We take uranium-235, we hit it with a neutron, it does a little dance, it splits into barium and krypton atoms, not the kind from Superman, but it's fun to think about it. And you end up with free moving neutrons, which then heats up the water around the reactor in the pressurized systems and gets those turbines to go. All right. So that's pretty cool. Capitol Hill, Seattle, they had a paper, September 6th. Okay, I will check it out. Now, I will say I haven't gone over every single accident that's happened within nuclear energy. But what I've read is there's been no deaths, no severe injuries. It's just people who have been exposed. Let's look at this other picture on greenhouse gas emissions per kilowatt hour. So if you look at your how much energy you use, I mean, this is how your power company determines what to charge you based on your kilowatt hours. Yes, 238 can also turn into, I believe it's plutonium. Is that what you're saying, PU? That's another, it depends on, there's two different ways that you can split, uranium. So there's two different ways usually that they use to split uranium. And I showed that a bit earlier in this particular talk. So if you want to hop back and look at that a bit, so I have a little graphic for you that shows how the two split, well, at least the two different ways that they do nuclear fission to generate energy using uranium-235. All right, so greenhouse gas emissions per kilowatt hour. So for every, let's see, so we've got approximately, let's say 850 grams of carbon dioxide are released into the atmosphere for every kilowatt hour. All right, so 850. That's what I'm kind of reading there. If halfway is 9, so that's kind of halfway to the halfway point. So about 850 grams of carbon dioxide is emitted for every kilowatt hour. So this entire talk is about an hour long, and the power for that is, if we consider kilowatt hours for my laptop, this light, the light above, the energy in my house, my, air conditioner that's going right now, 850 grams. All right, natural gas is about 500 grams of carbon dioxide per kilowatt hour for each hour of coal. Solar, considerably less. I don't even know how to read that. I can't, precision on this particular graph. It's just say it's very little. Nuclear, even less. Wind, even less than nuclear. So, that's kind of what we're looking at. And carbon dioxide in the atmosphere is our problem. Let's look at this particular picture on how many deaths are caused by the different types of energy. So we don't want nuclear because we're scared of all the deaths. Well, we're killing people right now, folks. So here we got the estimated impact of fossil fuels and alternative energy sources on human life. So every one of these people equals 10 years of life lost per trillion kilowatt hours of energy. All right. All righty. So let's see. All righty. So per kilowatt hour of energy produced basis here for this particular graph. So we've got the European Union and the Paul Scherrer Institute. This is the largest national institute that found an interesting trend regarding the fatalities that are attributed to each individual energy source. Now, I've pulled these graphics off of Harvard, so I'm just going to say that. So props to Harvard, for their particular information there, and you can check out that link as well at the end of the talk. So nuclear power is the benchmark to beat in regard to saving human life. It outranks coal, oil, gas, wind, and even, light is, coal, natural gas, wind. There we go. So we're not considering solar in this case because I guess they didn't investigate that. So it outranks all of these with just a slight margin with wind. So we have to consider coal and natural gas are kind of lethal to people when you compare it to nuclear. So some final thoughts on this. So digging down to my final thoughts, and then I'll catch up on the chat. At the rate we are going with using combustible fuels as our source of energy, we are going to change our planet, possibly permanently, at least in several generations of lifetimes. We are already eliminating species as we are now responsible for the current mass extinction that hasn't been seen since the dinosaurs. This is our doing. We must use new sources of energy, even if it is a scary sounding source, nuclear. Education is the most effective combatant for fear. Read up on nuclear energy and let's move from fear of change to taking hold of a better future for us and our planet. All right, so now I'm checking out the chat. Let's see. The free-moving neutrons is from Verillion. The free-moving neutrons also assist with the need for more neutrons to make fissile material. Is that missile? SM1 killed at least 2 back in the 50s. Okay. Taste the meat, not the heat. Oh, goodness. All right. Fuel manufacturing and costs and hams go ignored. Ask a tribal council. And harms go ignored. I don't know which fuel you're talking about. ScientistMel. Okay, Nana, I'll hit you up on Discord. My nucleus is decaying. Now I'm burned. And now I'm bummed. Your nucleus isn't decaying. Doc, you're funny. All right. Can China reduce its coal production as it is the highest consumer? They actually are working on shifting to more renewable resources and moving away from coal. That is something that they're actively working on, and it's in place. All right, so let's wrap this up and go back over the questions that we talked about. So let's wrap this up a bit. So nuclear energy, what have we talked about? We talked about what it is, how it works, the issues associated with it, and any types of criticisms. We've also talked about how it relates to other forms of energy. Now the breakdown. So that's the next one, the breakdown of it. The first station opened 1950s, and it provides 11% of the world's electricity from approximately 450 reactors. It's the second largest source of low carbon power. Over 50 countries currently use 225 research reactors, and it also uses uranium to make fuel. So, and there have been talks about that. So let me show you my sources. There's a whole lot of them. And if you can't read them all, that's okay. You can go to my website and kind of check stuff out, ScientistMel.com. Let's talk about where you can find me. Where can you find me? Everywhere on the internet. ScientistMel.com, Patreon.com/ScientistMel. I've had several patients hop in here. Doc Fearsome and Nana, thanks for being here. Cersei was up in here a little bit ago as well talking. So please, if you like what I do, throw me a couple of bucks each month. Patrons get early access to the audio versions of my live streams, the more interesting ones. Some of these are just like, oh my gosh, I've had so many technical difficulties, but they also get their own RSS feed that they can put into their podcast apps. They also get exclusive content. I'm on Periscope, YouTube, Facebook, and Twitch. And so we are going to wrap this up. This has been the science of nuclear energy. If you have questions or comments, hit me up in the comments section. We have a new show that's coming out, I believe, a week from tomorrow called Oral Audacity with Doc Savage. We had to postpone this Sunday's show because of the fact that he's traveling for his work. And so, you know, he does science, so that's kind of important. So he has to go and check that out. The shop, ScientistMel.com, where you too can be a cam girl for science. I also have an entire series just called Blocked By. It's my Blocked By series. And that's a particularly important series and close to my heart because I take horrible behavior on the internet, convert it to merchandise, and all of the profits go to charities. Currently, the charities that I'm contributing to are the ACLU, Planned Parenthood, World Wildlife Foundation, the Trevor Project. There's a trans rights activist group that I contribute to. I also contribute to the Anxiety and Depression Association of America. So go through, and I should list in the different products where those proceeds are going. And I do. I send them that money each month whenever I get purchases for that. Keep up with it, and then I send it over in to those different. I donated money to Planned Parenthood because somebody bought some flip-flops from somebody who is very anti-choice and who is not very nice on the internet, and she's been blocked by that person recently. It with honor. Be blocked by horrible people, and let's donate money to charity. And I have to say thank you to Peter, aka Gonna Go For It, for making a lot of those particular designs and decals that you see. Thank you, Bullionator. Bullionator has a Patreon. You can check it out. It's Bullionator, I believe patreon.com/Bullionator. He works for, I do pay him, so I want to make that plain. He and I have negotiated a payment of what I pay him every month to do work on this, and I will stick to it. And we can renegotiate at any time. The bigger the channel gets. We'll also talk about all of the work that he does. And do check him out if you can contribute to his Patreon. He helps me out a lot, and I'm so excited to have him here because now I don't have to worry about all the technical difficulties that I've had in the past because he's ace and he's got this. So, yay! Thank you, guys. I will see you next Saturday. Saturday. I'm trying to get together a new This Week in BS. So that's kind of a whenever I can get it together. And same with Spirited Science. And if you have suggestions for my shows, hit me up on Twitter. Use the hashtag HeyScientistMel or DM me because my mentions on average are anywhere from 200 to 300 per day. And I don't see everybody's comments. It's just sometimes my Twitter app and stuff does not actually show me all the comments. So hit me up there. Thank you, everybody. Thank you to my friends, and I will see you next time. Let me end with Mr. Rogers. You always make each special for me. You know how? By gesture being you. See you next time. Bye.